Hi, this is the second chapter of the Merriam text, and this is the part 1 PowerPoint or part A PowerPoint. So this chapter deals with chemistry, and it's broken down into two types of chemistry, including biochemistry. And so this is going to be an underlying theme for lots of different chapters that will help you, especially if you might be on the path to becoming a healthcare provider. So but chemistry, basic chemistry, and biochemistry are those two divisions. And we'll start with some basic chemistry. First, we have to talk about the different forms that things can take, including being a liquid, a solid, or a gas. And so this is anything that occupies space, and that's called matter. Matter can be solid when there's a definite shape and volume to the substance, liquid, or a gas. And we'll talk more about some of these, especially as we get into talking about water and how water can change between liquid and a gas and solid a little bit. But we'll talk a little bit more later about that. So, going into the second part of the chapter, all matter is made of elements, and elements cannot be broken down into simpler substances by just like simple chemical methods. And we'll look at several elements throughout the semester, but four of them make up about 96% of our body, including hydrogen, oxygen, nitrogen, and carbon. And by the way, their atomic symbols create the mnemonic HONC, H-O-N-C, and that's how I kind of keep that in mind. There's other elements in the body too, like zinc and magnesium and iron and all sorts of stuff. And so other elements make up smaller trace amounts. These elements are arranged into the periodic table, and the periodic table has periodicity, where we see different properties in different rows and columns of the periodic table. Elements are made of atoms, and atoms are just the smallest form of the element that has the same chemical and physical properties of that element. When we see the atoms listed within the periodic table, we see a specific atomic symbol for the elements, and that could be one letter or two, and sometimes they make more sense, like O for oxygen. Some are a little bit different, like Na for sodium, so that comes from a different language in the term for sodium. All right, so we'll skip through some of this, but there is some good information about these elements in your text just in case you want to look through those tables. But let's go back to atom. So in the last chapter, we said that atoms are the smallest, like least complicated level of organization, but there are subatomic particles. There's protons, neutrons, and electrons within atoms. And protons have a positive charge. Electrons carry a negative charge. And generally, when we look at elements that are listed within the periodic table, the number of protons and electrons in an atom is the same. Then there's neutrons, and they don't have much charge at all. Protons and neutrons weigh about 1 mass unit. You're not going to be tested on that, but that might make more sense in a second. Electrons are very, very small. So the number of positive and negative subatomic particles is pretty much equal. And so atoms are neutral overall just because the positive and negative particles is generally the same. Now, protons and neutrons are packed within the nucleus of an atom. It sounds kind of like a cell, but it's not. It's much, much smaller. And electrons hang out around the nucleus, and sometimes you'll see pictures like this that depicts the electrons kind of hanging out in these shells. If you've taken chemistry, you've learned all about valence shells and that sort of thing, and I'm not going to go into that much detail, but it may help you with some of the information about bonding and things like that if you have a background in that. But the protons and neutrons are within the atom's nucleus. So when we look at the periodic table, we'll see lots of different information, including the atomic symbol, but also the atomic number. And that tells us the number of protons, which we can assume is the number of electrons also. The mass number, and this tells us protons plus neutrons. And we are also later in this PowerPoint going to talk about isotopes And we're not really going to spend as much time talking about atomic weight, but your textbook will go into that a little bit more. So hydrogen, just to give you a little bit of a visual here, has 1 proton, 1 electron. I'm sorry. Yes, 1 proton, 1 electron. And we can see both of those here. And so the proton is supposed to be here within the nucleus, and it's got an atomic number of 1. All right. The rings or shells that you see here represent the electron shells. And what you want to happen with these, what atoms really love is for those outermost electron shells to be maximally full. So we'll kind of touch on that more in just a little bit. All right, so we talked about atomic number, we talked about atomic mass or mass number, and we can change the mass number. If you were to change the number of protons or electrons, the atom would be different, but we can change the number of neutrons, and that creates it's the same atom, same type of element, but a different version of it called an isotope. And by changing the number of neutrons, you change the atomic mass of the element. And so isotopes are just variations of the same element. And we could see from your textbook one isotope of hydrogen, or 2 examples of isotopes of hydrogen. And why do we care about isotopes? What does it matter? Well, when they break down or decompose, they do this more quickly. They give off radioactivity. And so this is beneficial in medicine in some cases because radioisotopes are really useful. For example, an isotope of iodine can be used to help visualize the thyroid gland, and that can help to detect cancer in diagnostic imaging. Any sort of radioactivity, however, can damage living tissue. Okay, so moving on, atoms come together and form bonds and form bigger molecules. Now, molecules technically are when you have the same kind of atom that are joined together. If you have different types of atoms, they're compound as they're formed, and mainly, you know, in this book and the things that we talk and kind of simplify, we talk more about molecules and kind of use it in a broader way. So not going to test you too intensely with that detail, but just keep it in mind. So most matter exists as mixtures, 2 or more components that are mixed, and this can create things like solutions, colloids, or suspensions. And so we'll talk about solutions first. And there's a good visual from your textbook. Solutions contain a solvent, and the universal solvent is water. This is a substance in a mixture or a solution that has the greatest amount, and it dissolves a solute. This could be something like salt or sugar. A solution, you know, a lot of times it's transparent, but sometimes we see color to it. But in most of the cases, especially in lab activities and things like that, you know, they're transparent for the most part. So here's just some examples, some descriptions of some solutions. I like this, especially when you get into ANP2 and you start thinking about fluid electrolyte homeostasis. The solution is going to involve concentration of a solute within the solution. And so when you think about the concentration of the solution, it relates directly to the amount of solute there are within that solution. What percentage of that solution is made up of the solute. And this will come up as we get into chapter 3 also, because this can drive the movement of solvent between areas, or even solute between areas. So more to come with that later. Colloids are also called emulsions. They have particles that are not evenly distributed throughout the mixture. And so you can see big solute kind of particles, and they don't settle out. So it makes it look not transparent, but more cloudy. And suspensions also have larger kind of solutes, but they do settle out. So if you've seen sand in a mixture with water and it kind of settles out, or even blood in a centrifuge test tube, you'll see the larger formed elements kind of settle to the bottom. Okay, So we've talked about compounds and molecules and mixtures, and I'm going to keep going into chemical bonds. So these are relationships between electrons, and they are not actual physical structures. They're just a way that the atoms are kind of held together in a molecule or compound. So as a reminder from earlier, and we're not going to go into specifics with how, the number of valence shells or valence electrons or the maximum amount in each individual valence shell, but just in general, I want to tell you that electrons are in electron shells. And the outermost electron shell hopefully is maximally full. If it's not, then an atom would like to fill it up in some way. And so that can lead to easier bond formation. And we'll talk about which type of bond in just a minute. And that outermost shell is called a valence shell. All right, I'm going to skip over some of this really kind of more in-depth chemistry information. Not that it's not important, but let's get into bonds. So just make sure you know these definitions of the bonds. In an ionic bond, we've got two atoms, and one of them has lost an electron, and so it becomes more positive. The other has gained an electron, and it becomes more negative. That one is called an anion. The one that loses an electron is called a cation. And so the relationship between these two atoms is an ionic bond. Another way to think about this is a bond between two oppositely charged atoms or ions, because an ion is an atom that has a charge. So this gives us a little bit of notes about what I just said as far as anion and cation. If you're a cat person, you might think about this as positive, P-A-W-S. Okay, moving on. We've all seen these classic kind of images of salt and ionic bonds between sodium and chloride. And let's talk about ionic bonds a little bit more. Ionic compounds, most of them are salts. And so these form crystals instead of molecules, such as table salt. Okay. Covalent bonds, on the other hand, happen when atoms share electrons. It could be one pair of them, or it could be more. And so this helps to fill the valence shell, maybe between both of the atoms. It could be one, we don't know. All right, it just is situational. And so this sharing can be unequal between the two atoms, and that's called a polar covalent bond. Or it could be an equal sharing between the two atoms, and that's a nonpolar covalent bond. And just to give you some visuals from your textbook, we can see some images of this where those electrons are shared. And so when you count them, you kind of give credit to both of the atoms as containing those electrons. So sharing of electrons between atoms. All right, so again, nonpolar means that they're shared equally, like in carbon dioxide. And with with polar covalent bonds, there's an unequal sharing. And so we see this in things like water. Okay. So I've talked about bonds. Your book has some great tables for this. And last but not least, hydrogen bonds. This is sort of like a covalent bond. It really is like a type of covalent bond because it is sharing of electrons, and it happens between a hydrogen and another atom, and it is a very weak bond. And so a lot of times it's represented with dashed lines like in this image. And this represents the fact that these are really easy to break and easy to form. And it helps water to have unique properties. And so your book talks about surface tension. So water is polar. Water also has hydrogen bonds. And these give it more unique properties that we'll talk about very, very soon. Okay, so let's talk a little bit about some types of reactions. When you have a synthesis reaction, small particles come together to form larger molecules. With a decomposition reaction, it breaks a molecule down. So this involves catabolic reactions. A synthesis reaction involves an anabolic reaction. Exchange reactions involve both of those scenarios. So bonds are made and broken, and there won't be really intense questions on these on the test. You may see anabolic and catabolic come up for sure. And then there are reduction, oxidation, or redox reactions for short. And so this happens when atoms are reduced. In other words, they gain electrons, and oxidized when they lose electrons. And so there's an example with glucose here. So let's talk about chemical reactions. We're going to see more of them in chapter 3 when we talk about things like membrane transport. But these different reactions can be either sped up or slowed down by temperature. So if temperature is higher, then generally it's going to increase the reaction rate and the kind of speed of that process. Also, the concentration. If there's a higher concentration gradient, it usually speeds things up as well. And if the particles involved, like the solute, are smaller, then there's probably going to be a higher rate of the reaction. And another big term that comes up with reactions is catalyst. And this is something that speeds up a reaction. You'll see proteins or enzymes that come up in this chapter, and we'll talk about different functions of those, and that includes acting as catalyst in reactions. I'll get part 2 posted soon, and please let me know if you have any questions.